Let's go over notes for 4.2 Part C, and in this section we're trying to find the exact area using limits. So let's first start off reviewing what we've done before with approximation. If we wanted to use 4 rectangles, for instance, to approximate the area between the curve, the x-axis 0 and 2, we see that we have some gaps that causes us to just be an approximation, and the way that we can improve this approximation is we can use more and more numbers of rectangles. Okay, if we use more rectangles, the gaps will become smaller, and we see that the approximation will get better and better. So imagine if we keep increasing the number of rectangles, we're going to get better and better approximations. Okay, so here I have typed out, we can continually improve the area approximation under the curve by increasing the number of rectangles. So we went from 4 rectangles to 8, and imagine if we have 16, we're going to get even less gaps, even better approximation. But now, what if we let n go to infinity? Okay, and if we do that, then if we have infinite number of rectangles, then we can use the concept of limits, and we not only have just an approximation, we're going to have the actual area under the curve, because if we can take the number of intervals to infinity, then there will be no gaps, and obviously we'll be able to get to the exact area under the curve. So here's the formula. Exact area is the limit as n approaches infinity, the summation from 1 to n for b minus a over n, this represents the width, times the height, and the height is f of a plus b minus a over n times I. So this portion allows the function to increment through each of the widths and then can be plugged into the function to get to the height. So this represents the width, this represents the increments of height for each rectangle. So to spell this out even more, okay, the formula is the limit as n approaches infinity, summation from 1 to n of width times f of left endpoint plus width times I. Okay. So an easy, or to break it down even more, what you do want to memorize is the formula being width times f left plus width times I. So width f left plus width times I. So here's my width, and all this represents the height of each rectangle. All right, so let's see if we can step through example 1. So find the exact area between the curve f of x, 4 minus x squared, and the x-axis from x intervals -2 to 2. So first step, we need to find the width. So the width is b minus a over n. So 2 minus -2 over n. So we're left with 4 over n. We're not going to be replacing n with any values, because we're eventually going to take this out to infinity. But we're going to hold on to this n value until we're ready to evaluate the limit. Okay, so we'll hold on to the n value. Okay, so now let's plug in all this into our formula. So area is the limit as n approaches infinity, summation from 1 to n, 4 over n, that's my width, okay, times f of a, my a is going to be the left endpoint. So the left endpoint, if we look at our interval, the interval says from -2 to 2, so my left interval is -2. So f of -2, okay, plus width times I. So my width we just found to be 4 over n times I, so we put that into the formula. Okay, so that's the first step. Okay, we're not going to do anything with the width, but we do want to get this out of function notation. Okay, so the way we do that is we're going to plug all this in for the x value for our function. Okay, so everything in the parentheses will go into the x value, okay, because we want to evaluate this function. Okay. So the function says 4 minus x squared, so we'll simply 4 minus parentheses negative 2 plus 4 over ni quantity squared. So that's what we have here. Okay, so that's the big hurdle we have to get over. We have to know how to plug this value into the function and thereby get it out of function notation. And so now we have a lot of algebraic work to do in order to simplify, get rid of parentheses, and get rid of the exponents. So let's look in here. We have binomial squared. So negative 2 plus 4 over ni times negative 2 plus 4 over ni. We take this, we're going to square it, or multiply it by itself, and we're going to get 4 minus 8i over n minus 8i over n plus 16 over n squared I squared. Okay, this is still in parentheses, and I'm going to distribute the negative through to get rid of the parentheses, and the 4 minus 4 cancels out. These two terms combine to be negative 16i over n, but the two negatives will cancel out, leaving me with positive 16i over n minus 16 over n squared I squared. Finally, distribute the 4 over n through, and I'm going to get 64i over n squared minus 64i squared over n cubed. Okay, so now this should remind us of summation formulas that we've seen before. We want to pull the coefficients in front. Remember, n is a constant, and we want to isolate the portions that where we can apply the summation formulas. Okay, we have summation of 1 to n for our value I, and we also have a formula for summation from 1 to n of I squared. Okay, so summation of I gets replaced with n squared over 2 plus n over 2. Let's see if I can pull this up a little bit more. Okay, and then summation of I squared gets replaced with n cubed over 3 plus n squared over 2 plus n over 6. Now I'm going to distribute everything through, and now we're just going to find a limit as n approaches infinity by comparing degrees between numerator and denominator. So all the ones I canceled out are going to go to 0 because the denominator's degree is higher. So we're just left with 64 over 2 with the same degree and 64 over 3 with the same degree. So 64 over 2 is 32 minus 64 over 3. Find a common denominator, or you can plug in the calculator, and you're going to get area of 32 over 3. So the exact area between the curve, the x-axis, and our two x value intervals will be 32 over 3.